of this FDP and session 7, Dr. Yelakandan Rajamohan sir, Assistant Professor IIT Goa, on behalf of Lendi Institute of Engineering and Technology and AICT ATAL, we welcome you, sir. Now, I request Srimati M. Sujata Madam, Assistant Professor, Department of ECE, introduce the speaker of this day to the audience.
Hello. Thank you, ma'am. Ma'am, I'm audible? Hello.
Yes, madam, you're audible.
Yes. Sir. Good morning, all. This is Sujata, Assistant Professor, Lendi Institute of Engineering and Technology, Department of ECE. It's my privilege to take an opportunity to have a profile of today's speaker, Dr. Neelakandan Rajmohan, sir. Dr. Neelakandan Rajmohan, working as an assistant professor in the Department of School of Electrical Sciences, Indian Institute of Technology, Goa. His primary interest areas of research in signal processing in 4G and 5G cellular networks, spatial modulation, massive MIMO, broadband spectrum sensing. He received his PhD from IIT Madras. Prior to his job, he worked as a faculty on IIT D&M from July 2017 to June 2018, Chennai. And so let us welcome Dr. Neelakandan, sir. Sir, from the Department of ECE and from the management of Lendi, we all welcome you, sir. Thank you. Thank you all.
Yeah, thank you very much for this very good opportunity to interact with you all. So I think let me start my session. So good morning to all. And first of all, I would like to apologize to bother you all in a bit early. Actually, the session was scheduled at 10. Since I have back-to-back 2 sessions continuously, I thought to start it slightly earlier so that I would be having a little more gap in between the sessions. And plus, I will be going in a slower pace so that if participants would like to join subsequently, they won't see such an interruption or abrupt change in the contents. Okay, so let me start the sharing the screen.
Share it with space, sir. No problem.
Yeah, is it fine now?
Sir,
Okay.
yes, sir.
Yeah.
Yes, sir, it's fine, sir.
Yeah, thank you. In case if my any problem in my audio clarity, just text me. I would be taking care of it. Yeah. Okay, so today let us start with. I have 3 sessions in this FDP, so I would like to cover in such a way that I could give emphasis on certain things in a very good shape, rather than to connect everything in bits and pieces. So I have arranged it in such a way that these 3 sessions would offer you a kind of flavor of where these 5G technologies go ahead and how we are going to align our research and directions along with that, and some interesting lines of research where we could pursue. So the very first point I have taken in this lecture is on the millimeter wave and massive MIMO communications. The amalgamation of millimeter wave and massive MIMO is one such kind of interesting thing the researchers and the scientists would like to take it over, because these two have some kind of inherent connection with each other. Let us see subsequently. And yeah, so this is just one screenshot. Yeah, for within 60 seconds, what is happening all around the world. So in terms of different internet transactions, let me call it as internet transactions, like how many YouTube videos are uploaded, how many hours of videos are being watched, and how many internet transactions going on, and like Facebook, Twitter, Netflix, and WhatsApp, all the things. So what is going on within 60 seconds. This is taken from the source given below, like how much that is showing that how much we are binded with internet nowadays. So earlier we have the internet maybe in the internet center or browsing center. Some all the way now we have at least starting from our mobile, wristwatch, everything is connected to internet. So we are making the more and more demand for the internet related services, and also that data speed we require, the privilege of watching more, faster downloading and so on. Like, so that is forcing us to go for some, keep on changing our wireless evolution technologies for higher standards. So that's why we are from starting from 1G. Now we are at the 5G. Just we are going to step into 5G very soon in India. So we are expecting that by mid of 2021. Earlier that was expected in mid of June of 2020, but due to COVID pandemic, things slightly differ. Yeah, nevertheless, we will see what are the potential technologies we are trying to see in the 5G. So now the slide is showing that what kind of evolution we have been on the way from 2G, 3G, 4G, now at 5G. The 1G is not put into the picture because 1G doesn't have internet. Only from 2G onwards, we have started to have the internet in our mobile. Anyway, so I will brief about these generation technologies in the subsequent slides. So starting from the 2G, the picture shows that how we are evolving and how much data hungry devices we get involved with. Compared to 4G, in 5G we have 100 times mobile data and 10 to 100 times connected devices. The term connected devices is that like how many number of devices that need internet by one way or the another. And the latency is the delay for the minuscule transaction from end-to-end transaction. So lower latency. And what is the end user data rate? How much the user can experience on an average? What is the data rate or download speed that can guarantee to the users? And what is the battery life? Of course, this is like a challenging task. More and more we are going for advanced technologies. The battery would last for at least 2 days if you make it a full charge. Now with the internet connection and so on, that hardly lasts for 6 to 7 hours. Right. So then this is one vision, like how do we expect and how do we evolve towards 5G? And so what kind of services as a 5G will provide and what we can expect from that? So we say 5G, so what is the difference? What we are expecting from that? The first one is the multi-domain performance and the energy performance. And we are trying to make a global standard. Rather than if you take your mobile to another countries, you may have to register another SIM card and you have to buy an international SIM card to roam around and enable that, or else from your internet or data service provider or network service provider, you have to request for international roaming and so on. So all these things happen because the different standards followed by different countries. So we would like to make one global standard such that we have a seamless transition from one place to another. And in more particular, 5G is not about only the mobile technologies, that is even touching the industry side as well. So what we call as industry 4.0. So how much we can make the productive in the industry side with the 5G technologies. In earlier, we talk about these 3G, 4G and all only with respect to wireless communications. So they had nothing to do with other industry or other applications. But now we are trying to integrate everything together in such a way that the 5G is only not about the wireless technologies, that is also about industries and applications, unlike all these empty hexagons, which is showing that still they are under development, like massive type, machine type of communications and mass market on the personalized televisions. And all these things are being developed such that 5G is not only about wireless or mobile, that's also about each and everything in the technology and engineering side. So let us quickly go through what we have been from different generations. See, and I would, in this both this talk and as well as the subsequent one, I have minimized the mathematical details. Anyway, within 1 hour, I can't go in depth into the mathematical analysis. Nevertheless, I would give you the right references and directions to pursue. If at all you are interested or you are a person who is doing research in wireless communications. So I am going to give you only the big picture of what is happening uh, to minimize the mathematical details. Okay. So I will give so that you can expect more on the figure side rather than mathematical discussions and equations. Except I may have very few at the last, so that I could address those audience who are working or doing research in wireless. So let us quickly go through from 1G to 5G. So the generation tells the label actually. So a particular generation covers a particular set of technologies. Now under 1G, what are the technologies we had, how it was developed, and when it started, when it became obsolete, or when it got rid away from our usage. So in the 1G, it was developed in the early 90s and completed in the early 90s. So 80s and completed in the early 90s. So 90, we have the fullest deployment of 1G technology. And the 1G standard based on analog system. And I hope those who are working in communication side would be able to differentiate the analog and digital side. Analog is like we don't have the digitization technique of the voice and all the information. And the speed up to 2.4 kbps. Of course, one might ask that we are saying analog and what about this kbps? This is only for the control channel transmissions. When we press the numbers in the mobile, so that works under the principle of DTMF, dual tone multi-frequency. So how this data is converted and what is the speed, that's what it says. And that was under the standard of advanced mobile phone system, which was developed initially by US, and that is how we had the 1G mobile system. You might have remember this kind of a bigger phone with one big antenna. So that is where we first started to develop mobile phone. From the line phone connection, we have first usage and application of commercial mobile phones. And at the time, it was very sparse usage in the sense that maybe one or two in the 100 would be having a mobile phone, not everyone, of course. And the main drawback, not drawback, let me say that as a limitation. So the limitation of that 1G standard was that you can use the mobile phone only within your country. In layman terms, you cannot make an ISD call from your mobile phone. Of course, you can make STD call if at all you have subscribed to that from the mobile. And thus that won't allow you to make international calls from your mobile. Interestingly, 2G, the very first time, I hope many of you might remember a mobile phone that comes with a SIM card. So there were two kinds of cellular phones you might have come across. Not inbuilt, that identity is inscribed in that, like it is integrated with the system. So that is what we call it as the CDMA, code division multiplexer systems. And another one is GSM. Yeah, we will see the technology names and some technical information about that. So very first time we have started to introduce the digital system into the mobile telephony, and the speed that was supported was up to 64 kbps. And we have services such as digital voice, SMS. The way before that, people were using the pager devices, and then we have we have started to have the short message service protocol, SMS protocol in that. And once SMS started to be integrated in that 2G mobile phones, the pager started to become obsolete. And still we are using 2G standards. Maybe our parents and some elderly people may be comfortable with this kind of phones, 2G mobile phone rather than our 3G, 4G and the touch screen and all. They may be a bit comfortable in these button phones. Still we have that. It is compatible with the 4G, 3G and 4G network. But still the question is, are they compatible with 5G? We will address that question later. And there was another intermediate standard that was developed, which was referred to as 2.5G. That has more capabilities. We will see the technical details about that shortly. And then in the early 2000, but at least until 2010, I guess, it was under development, and we have started to use the 3G mobile phone. Now, at least most of the coverage now is under 3G. except in very few urban places and metro cities, we have 4G connection, but not throughout the country. Still, there are several places which have only 3G, and of course, they are still in 2G as well. And the data rate is up to 125 kbps to 2 megabits per second, and the superior voice quality. And very first time, the video conference was enabled in the mobile phone. Nevertheless, I hope you might have tried. If you try to make a video call in 3G mobile phone, most of the time that won't support. Yeah, because of the high data rate and high quality pixels and so on, that rarely supports video call. But still, that was enabled, but we couldn't use that at the fullest swing. And very interestingly, all the email app, online shopping app, banking, games, everything started to develop in the mobile phone, which led to the difference of and other Android based, they have started to develop different apps for the mobiles. Rather than online shopping, if instead of going to the flipkart.com website, people have started to develop app for that. But sooner what happened, all the commercial information have started to develop in terms of app, like Ola, Uber, everything now becomes in the app. But this is the pioneer development of that at the 3G. And in 4G, yeah, developed in 2010, and then after that we have started to use very recently, that has been deployed widespread and faster and more reliable. Now we have the very good high quality video calls, not only through the voice network, and also we have data network, voice over IP and so on, our WhatsApp video call. So now we have so many other apps and internet services which support us to make video calls seamlessly and with very high quality. And we right now we experience a speed up to 100 Mbps on an average of 15 to 20 all the time. You can test with your speedtest.in or several data speed measuring networks and the websites are there, where you can check your upload and download speed in your mobile phone. Right. Then let me come to the 5G, and we are going to come to that theme of our FDP and what we are trying to see. Yeah, sorry. So this is the next major phase of the mobile telecommunication and the wireless systems. Now we will be able to see a lot of drastic development in the 5G, starting from your device, the way you are using your device, and the material advances in the material sciences. Like your phone may be looking like this, like a glass plate. A transparent glass plate may be the ideal, and people are foreseeing for such a kind of device for the mobile. So in the 5G, not only in the wireless side, the technological development from various aspects are coming into the picture. And we are expecting the speed of up to 1 gigabits per second. And it is more faster and reliable than 4G. And of course, lower cost than the previous generation. Of course, that will be taking some time. During the initial deployment, the biggest problem in India is the investment. So we have very less number of startups. Now we are being encouraged to get more and more startups and so on. So the cost will come down only after widespread usage of the 5G technologies. But initially, the 5G phones and everything cannot be that much economical at the market, at least compared to the 4G mobile phones. Right. Let us have some technological terms to just keep our audience who are working in the area of digital communications and wireless communications on the track. So let me come back to some technological terms in that. So the technology 1G, 2, 2.5, 3, 4, and 5G, and what is the deployment year, and what is the typical bandwidth that requires, and what is underlying technology for the communications. Like in 1G, we have analog cellular, 2G, we call it as a digital cellular, and 3G, the communication started to take place with the broadband bandwidth. The internet network supported to have the communication. And now in 4G, we have unified and the combo of all the LAN, WLAN, wide area network, and personal area network, and so on. And one kind of service that can offer. In 1G, you can simply speak in the phone. It's a mobile telephony. Instead of standing in a particular place or being idle, with your landline phone, you can just speak and walk. That's what 1G phone offers you. It's just a mobile telephony. That's it. But in the 2G and 2.5G, we have started to have digital voice, SMS, short messaging, and so on. And 3G that started to support integrated high quality audio, video, and data, which has been still enhanced in the 4G. And now we have variable devices and services in 4G. Of course, we know starting from app and everything. And what kind of multiplexing, how multiple users are supported. In 1G, that was about FDMA, meaning that every user will be having a different frequency for communication, frequency division multiple access. Whereas in the 2.5 and 2G, we have TDM, the hybrid TDMA CDMA mode, where TDMA stands for time division multiple access and the code division multiple access. And we remain to use CDMA, and 5G we have multi-carrier CDMA, OFDMA, and so on, other techniques we have. And switching technique, how do we connect different? For example, we cannot have every user pair, you cannot have one dedicated network. So we have a network pool, all the users are connected to the pool. So how do you connect from one user to another? That's what the switching techniques tells you. If that is circuit switching, that tells that every user have dedicated work communication path. All the data will follow the same passage. That is the circuit switching. Where in the packet switching, the data will be fragmented and thrown on the network. Each packet will find its own way to reach the destination. And again, of course, the receiver has to rearrange the packets to get the actual data or actual information transmitted. So now we have started to migrate from circuit switching to packet switching. Now it is all packet switching. And more importantly, what is a core network that supports that? Earlier we have public switched telephone network, PSTN. So all our mobile phone and our landline phone, everything was integrated with the backbone PSTN network. Now we have started the packet switching. So our internet is the backbone network. Now everything is connected with the internet when you use 5G. Now some of the technology names, what we have been using in different standards. These standards telling you that how do you get internet in your mobile phone. So these technologies are responsible for how do they give you the internet in your mobile phone. Your mobile phone was initially meant for just a mobile telephony, like giving you the voice services over the phone. Now we are using the internet in the mobile. How? So what kind of technologies that offer us? In 2G, internet was from general packet radio service, GPRS technology. And 2.5G, the technology that was helping the mobile phone to get access to the internet was exchange data rate for GSM evolution, where the speed is up to 473 kbps. Sorry, this is kbps. I will correct it before uploading the slide. And in 3G, we have high-speed packet access network, HSPA and HSPA+. That is what we refer to as 3G, and where the data is up to few Mbps. And next, this wireless LAN is nothing but to get the internet within a room or building, that what we call as Wi-Fi in the commercial terms. And LTE is a long-term evolution. That is what we are using in the 4G standard, where the speed is up to few hundreds of Mbps, and where we can make video calls. And the WiMAX is a competitor of LTE, but what happens, such a limitation of WiMAX stopped its widespread deployment in the 4G. Though 4G, both WiMAX and LTE were the potential candidates for 4G, LTE slightly surpassed the WiMAX in terms of widespread deployment. Now all the letters in red in color, I have written here that you must be able to see in your mobile phone. If you see the symbol either 4G or HD, you are connected to LTE network. The HD you will be able to see if you enable the option in your settings, use high definition voice. If you go to settings and check for the network manager, you will be able to see there will be an option. Use high definition voice quality, HD option. If you enable, you can see that. If you disable, you will see 4G. If you are connected to 3G, you will see either H+ or H. If you go to any villages or remote places, you will be able to see the E, meaning that you are connected to 2.5G network. 2G is still there, but if you go to very far remote places in term like a hill area and so on, you will be able to see the 2G. Right now, somehow we are connect out at least to 3G in many of the places. So the EH plus are most common places, and almost to some extent we have deployed 4G as well, right? Then now what is 5G is all about? That is about just integrating all these internet providing technologies in a single framework. So your 5G terminal must be able to get connected to GPRS, get connected to 3G or WLAN or LTE, whatever it is. That will ensure the backward compatibility, in the sense that you cannot ask all your consumers to throw away their mobile phone, buy a 5G phone. If you are offering a 5G service, the existing users who don't want the 5G, they must be able to remain as their own. We are not supposed to ask them to throw away the terminal and buy a new mobile terminal. So that is what the condition main part. How to integrate all the things, so that you will be having a multi-bandwidth data part, in the sense that if I am using 5G, say you are using 4G and some other person with us with 2G, we will be able to cater their own needs and requirements according to the QoS they have been guaranteed. So within a single high capacity network, we are supposed to have so many different data paths, which each one has its own bandwidth. So that's what we are expecting and we are targeting in 5G. So let us quickly see the features. What do we expect in the 5G, and what is a description on the features, and what are the potential technologies that guarantees these features. So that is how these three columns are arranged. Let me just go through a few of them and leave other things for your own reference. And for example, the data rate, what we typically measure or experience from the end user. So the data rate, the description is about what do we expect. It must be at least 10 to 20 times larger than the 4G speed. Okay. If we have access to that, what technology that guarantees these things? One is operation of the millimeter wave band, and go for massive multi-input, multi-output technologies, massive MIMO technologies. And second feature, what is the number of connected devices? Meaning that if you take 1 square meter or 1 square kilometer, how many number of devices connected to internet? See, typical 1 meter square is our house. So how many typical devices in your home that would be connected to internet? So the certain statistics and measurement says that by 2025, once the 5G is full swing in the global and in our country, at least we can expect 7 devices in your home, at least 7 devices in your home that need internet. Right now you may have 1 or 2, maybe your laptop, say your mobile phone, and some people might have internet TV, right? So now say you are having 3. Now the development will lead to a path and land you at a place that where you have at least 7 devices in your home which need internet. Okay. So such a number of high connected devices, how should I manage? What are the technology that allows me to do that? One, IoT stemming, IoT and massive M2M communications, and very interestingly, D2D communications, device to device communications, and wider bandwidth dense small cells. If at all you develop these technologies, that will support this. That's what the interpretation of these columns. And I will come back to this D2D communication later. I will just get in touch with that in the later part of the slides, but we will see the other technologies as well. The spectral efficiency, bits per second per hertz. So how to interpret that? If I give you 1 hertz bandwidth, okay, what is the bits per second you can communicate? Let me take a simple scheme. I have given you 1 sine wave. So how many bits you can communicate? For example, with 1 sine wave with polarity change, plus and minus sign, say you are communicating 1 bit. So then the spectral efficiency is 1 bit per second per hertz. Now, the Shannon theorem says that what is the maximum capacity we can achieve. So we have a lot of coding theory and information theory aspect, how we can get close to the Shannon's limit. So like turbo codes, LDPC. Along the lines, we have some other waveform coding techniques like filter bank multi-carrier waveform, NOMA, non-orthogonal multiplexers, coordinated multi-point communication, COAM. This is our another talk in this today's lecture, cooperative multi-point communications. Like that, these techniques are to address the spectral efficiency aspect of the 5G. And again, end-to-end latency. I don't want to experience a lot of delay in my transactions. So how should I do that? One, let the device to device communicate. So what does it mean? Let me just give you one use case of this. Say, for example, you want to set up a kind of a thing in your home that when you wake up, say 6 o'clock, if at all you are able to wake up at 6 o'clock, your television should switch on automatically, say for instance. Now, if the conventional network, suppose if you have a sensor in your home that which is sensing that you have waken up, and that triggers the GSM module, that SIM card will give a message and television is switching on. Let us say this is one protocol you can develop with the ZigBee and IoT, right? Now what will happen when when you integrate it with the GSM, what happens? The sensor triggers that information has to go back to the tower outside your home, and that tower has to give the instruction back to the TV in your home. Now this is what incurring the delay. Now just your say your wristwatch to television, this communication has to take place from your wristwatch to tower back to your television. Now the D2D tells that what if your wristwatch and your television directly communicates with each other? Can I do that? That is what the term device to device communications. All those devices that are connected to internet, what if they communicate with each other? Can I do something for that? That's the question. Of course we can make it, but that is not as straightforward as we are discussing now. Say for instance, the devices have to determine when they have to communicate directly, when they have to communicate to the tower and so on. So developing such a protocol is slightly challenging. Anyway, still people are working for that, right? Now the data processing speed about and like what is a processor speed and so on. And again, for the speed, we have the D2D communication and NFV, network function virtualization. I think I won't have much time to discuss these factors. And the energy efficiency, interestingly about the battery life. And massive MIMO in conjunction with the millimeter wave band. This is one interesting combination, as I said in the beginning. That is what we are going to discuss in detail then in today and tomorrow's and as well as go. I think all of your talks are somehow aligned with these technologies. And finally, mobility. What is the speed you are going to use? See, that is an interesting evolution we have. Initially, the mobile phone was invented to give you the mobile telephony, meaning that you don't want to sit and talk with a landline phone. Even if you want to carry your phone or wherever you go, you want to have the mobile. That is what mobile telephony was meant for. So that is why people started to do the research. What is the maximum speed the user is allowed so that they are communicating? Suppose if you take your mobile phone and speaking over to a person and keep on traveling in a car, beyond certain speed, that depends on where you are traveling. For example, if you travel in a highway where you have a row of towers, so automatically the handover will happen when you move from one place to another. But if you are moving very fast, the towers cannot handle the handover quickly without any seamless transmission. Then automatically a call will be dropped and then you have to make a new call again. So this is what called call drop and handover. Hope you might have learned in wireless communications. But right now people are not worried about speed much because we are looking for high speed devices and high speed services at our home. So now essentially speed is of our lesser concern. The number of people or number of consumers, they would like to use the internet while traveling in a very high speed bullet train. We are not worried about them. We worry about them, the people like you who are sitting and getting a streaming video, how to make it effectively. Suppose if I switch on my video and if you ask all the participants simultaneously switch on the video, your data network cannot support that. Suppose if at all you have connected to internet with your hotspot in your mobile, it will be exhausted very soon. So we are worried about these concerns, not like the very high speed bullet train, how to give internet there. Of course, there are certain technologies which give internet access to such a high speed bullet trains, that too again from millimeter wave beamforming and all. Anyway, I don't have time to discuss that part, but just check in internet, like high speed railway systems and internet. So there we will have some kind of a Wi-Fi network within a bullet train, how to develop that and so on. Anyway, so this is just I want to give a notion of this point. Now, these are all the potential technologies on the third column that are viable and feasible that can give you the support and all the features what you are expecting in the 5G. Now, in one talk or another session, you will be learning any one of these technologies. either in terms of hands-on or theoretical lecture and so on. But our 5G, all the technologies will be focusing on this part along with other periphery like artificial intelligence, IoT, machine learning. These things are coming together to synergize among themselves and give us the fullest services from the engineering side, right? Now, where we are, the capacity improvement technology in 5G, how you can improve your capacity. So out of all the features, I'm able to take one or two of these and explain the corresponding technology where the millimeter wave is involved. So that is how the rest of the talk is arranged. And of course, we will come to cooperative communications and broadband spectrum sensing subsequently. Right. So if at all you have to improve your capacity, what can you do? One, this is your current capacity and say this is what you require in 5G. Now, there are three different aspects or three different degrees of freedom you can increase your capacity. One, increasing the transmission bandwidth. Okay, I give you more bandwidth, go and do that. Second, spectral efficiency. Another way of improving the capacity is given the same bandwidth, how can you increase the bits per second as we have seen in the previous slide. Third direction, frequency reuse or spectrum reuse. Use the same band different times at different places. How do you manage that? So if at all you have to improve the capacity, you have three different ways of doing that. One, have larger bandwidth. Another, given bandwidth, have a better data rate, find out some technology, or use the same bandwidth at different places. So these are all the three different ways you can improve your capacity. So along with the three different directions, I have given the examples of the technology which work under the principle. For example, spectral efficiency, how to improve the bits per second or data rate given the bandwidth. So massive MIMO, NOMA are the potential candidates for that. And if at all you have to go for high transmission bandwidth, then go for ultra wideband, go for millimeter wave communications, or go for cognitive radio. And if at all you have to use the spectrum at different places, yeah, when you give the same frequency to different users, you should know how to cancel the interference, or how to make them cooperative, or how to connect massive devices within the same bandwidth, how to predict the traffic, and then how to offload and manage your traffic. So these are all the techniques and challenges that comes under with the three different ways of improving the capacity. So now, out of the three different ways, we are going to touch this part, high transmission bandwidth, where who is going to give you more bandwidth, where you have to go, how you have to operate. So out of the three directions, we are addressing this direction. Maybe all other things, you may be one way or another, you might learn in other sessions in this FD, right? So just I'm telling you the big picture and I want to show you where you are. So out of the, as I already said, out of the three different directions, which can be interpreted as a time, frequency, and code ways, we are going to see the millimeter wave communications, which offers you a vast spectrum of bandwidth, where it is free and how you can make use of it effectively. Because the bandwidth we are using now is called microwave bandwidth. We are almost exhausted with that. So how we are going ahead of it, that's what it's all about. Now, this is the spectrum you might have seen in several places. Just I want to tell you a few things about this. Now, the red in color is completely occupied band. The green in color is where you can go and occupy. Blue, partial occupation, and purple, slightly moderate than this. Now, the band we are operating now is referred to as sub 6 gigahertz bandwidth. So we are now all our communication happening in this band, right? We don't have any technology that is going beyond this. So we are just operating in this band. Our wireless, even Wi-Fi, suppose if you are using a Wi-Fi router at your home that is operating at 5 gigahertz Wi-Fi band, right? Now then what is the millimeter wave band? First of all, I will come for the millimeter wave later. We are starting from 24 gigahertz to 100 and then 100 to 300. This has been fragmented into two different bands. And already out of the 24 to 100, an enormous amount of experiments have been conducted and found that these are all the bands where you can communicate based on the attenuation characteristics of the wave. So, okay, I have to tell you one more thing. See, the millimeter wave is operating at the very high frequency. Without going in detail all the things, let me tell you one thumb rule. More and more you are going for high frequency, the attenuation is very high. If you are going for the lower wavelength, attenuation will be low. Okay, say for instance, if you compare AM and FM, okay, if at all you have the old radio in your home, you can listen to AM radio even from Malaysia AM and so on. But if you have the FM, okay, that FM is restricted only to the city, like Erode FM, some Chennai FM, and say Hyderabad FM and so on. That is because FM is operating at a high band, high frequency band. So when you go for high frequency, the signal attenuates quickly. Now we have the something technology known as radio garden. If at all you don't have come across the word, you just type in Google radio garden and or you search in your Play Store for radio garden. You will get an app. So that app is connecting to all the FM stations across the globe. You can listen to FM of any country, any place. Even Dubai, Europe, wherever you want to go, you can just go and check. That is because all the FM stations are connected to internet. That satellite again transmits back the data to you. So that is how now we are able to listen to the FM radio of any station across the globe. If at all you have not tried, you just try that. That's a very interesting app that will show the globe with a lot of stars embedded on it. And you can pick one light, every light corresponding to one FM station. You can pick a light and then play it out. So such a wonderful thing was developed by ISRO, the radio garden. And you just check that with the Play Store and as well as internet. Okay, why I am saying that when you go for higher frequency, the attenuation is very high. So out of the available band, you have to find the one which offers a reasonable way of allowance to you to communicate. So that is how these bands have been identified. Now we have one unlicensed band at 60 GHz, meaning that you can go and communicate. Nobody will ask you questions. How to use that? Do we have technology to directly go for high frequency? No. All the antenna developed, everything was built based on the sub 6 GHz bandwidth. Suddenly going from 5 to 500, we don't have the technology. So our technology is not scalable in terms of the operating band. So how to do? That is what we are going to learn. How to address these challenges. What I have to do to cater that. Now, this network densification we will come later, but just I want to tell you because of the attenuation nature of the millimeter wave, where we have seen that the signal cannot travel for a longer distance. What will happen? Now we have one single tower which is covered in a hexagon we plot because so that you can pack like this. Typically that's a circle, but if you plot circle that may have either overlap or holes in between them. So that's why we plot in terms of cells so that we can easily pack and analyze that. Now typically what happens if you have a tower that can cover up to 5 kilometers in case of rural area, and typically in cities up to 1 kilometer, meaning that every 1 kilometer you will have another tower. Now because of the nature of millimeter wave, every 200 meter you may have to need a tower. In your institute building itself, you may have one tower, and if you go from one building to another building, that will be having another tower. That is how you have to do if at all you want to employ millimeter wave band for communications. So such a thing actually paves the way for very dense network. Okay, whether that is plus or minus to me, we will see that. Now another aspect is that massive MIMO. But why massive MIMO has been addressed along with the millimeter wave? That's a very interesting point. I will come in the next slide. Now instead of 2 antenna in your mobile phone, you may be able to have multiple number of antennas in your mobile, and the transmitter will have 1,000 number of antennas if at all you are able to operate millimeter wave. And if you have many antennas, you will be able to form a virtual beam to any user whom you want to communicate. So this is the technique what we refer to as beam forming. I will come to this part in the later part of the slides. And as I already said, now the current band is in the microwave band where we are operating around 600 megahertz. And now we are migrating not actually 3 is in the kind of gray area. Typically that is from 3 to 300, but above 6 is taken for millimeter wave. And we call this as millimeter wave frequency because the wavelength of this wavelength is nothing but light velocity divided by the frequency. If you divide, the answer will be in the millimeter. So compared to microwave waves, millimeter wave operate a very high bandwidth, so they have very lower wavelength. Of course, there is some caution. compared to microwave, millimeter wave has a lower wavelength. But don't think that this is millimeter, this is micro. Actually, this is 10 power minus 6, this is 10 power minus 3. So then don't expect this is having lower wavelength. No, there is a slight, you have to be cautious in the terminology. In millimeter wave, millimeter tells a wavelength. But in the microwave, micro is not the wavelength. Somehow that was named as microwave, I don't know. But in the micro doesn't imply the wavelength. Wavelength of the microwave wave is in the order of meters. Wavelength of the millimeter wave is in millimeter. So the micro is not the wavelength. Okay, so then people should think that this is smaller than that. Then this is supposed to have lower wavelength. No, the wavelength of this microwave is meter, in the order of meters. This is in the order of millimeters. Okay, now we have found out different feasible band as I have shown in the previous slide, 28 to 30, analyzes around some 60 gigahertz, and what we call as E band, 71 to 76, 81 to 86, and 92 to 95 in gigahertz. But operating in this bandwidth or in this very high frequency is completely a new paradigm. So what do we expect? Let us think about one aspect of it. One is that whether that is beneficial or not. Yes, one way it is beneficial. Excuse me. More and more you go for the higher frequency, the signal becomes directional. Like for example, in the laser light, if you point the laser light towards a direction that has more directional nature, that won't diverge. So that is one advantage of operating at the higher bandwidth. Higher frequency signals have more directional signals, but attenuated logs. And they have smaller wavelength. Yes. Okay. What is the advantage of smaller wavelength? You should know another information about that. Suppose you want to get benefit over multiple antenna. Say for example, okay, you have one antenna in your home. I allow you to have 10 antenna in your mobile phone. Okay. So can you directly get benefit out of that? Yes or no? Yes. Only if the spacing between the antennas is greater than lambda by 2, where lambda is operating wavelength. Meaning that if you have to place two antennas, at least minimum spacing between the antenna must be lambda by 2. If you are if you have so-called correlated fading. So because of the correlation, the two antennas will not give you any beneficial effect. Okay. So essentially what I am trying to tell you is that for the given operating wavelength lambda, at least the spacing between the antenna must be lambda by 2. Okay. Now another point. I have already told you that compared to the microwaves, where the wavelength is in the order of meter, millimeter wave, the wavelength is in the order of millimeter. Now in the microwave band, we are able to place two antennas in your mobile phone. Okay, provided with the condition that the spacing between them is lambda by 2. Right. Now your LTE, you have two antennas in your mobile receiver. Your mobile phone has two antennas. Now in the same lambda by 2, since the millimeter wave frequency, which is 1000 times lesser than that, now your mobile can have 1000 antennas in the same space, isn't it? So that is what the massive MIMO. So automatically, in the wave where you have the two antenna in the LTE band in your mobile phone, in the same space, backside of your mobile phone, in the same chip board, you will be able to place thousands of antennas if you operate at the millimeter wave. So that is what we call it as massive MIMO. Now, the amalgamation of between or the synergies between the millimeter wave and the massive MIMO is inherent nature of it. So that comes by handy to you. That is what one of the very important feature of millimeter wave, and where that allows the massive MIMO. Now people start to think about, instead of two antennas, if you give me 1000 antennas, what are the different things I can do? That is what one research direction on massive MIMO. In the massive MIMO, we have a lot of technologies. If you give me 1000 antenna, what can I do? Oh, I have to think about it. I can do a lot of things. So that is what it's all about. Massive MIMO. Yes. What is that? few thousands of antenna in the transmitter and hundreds of antenna in the receiver. That is how your 5G mobile terminals and 5G ENB or base stations will come up. And the number of antennas at that base station is greater than number of devices, of course. And the need for conformal array antenna. This is something about the smart array antenna techniques. And some of the challenges is like a pilot contamination. And though you have the spacing between the antennas lambda by 2, sometimes they create correlated fading, how you fabricate the antenna in your board. And something which we refer to as diversity outer saturation. Anyway, these things are quite more technical in wireless communication. Let me skip discussion of this point. Okay, and before I have proceed further, those who are not familiar with some of the terminology which I will be using subsequently in this lecture and the next 2 lectures, I have given few slides what I mean by SISO, MISO, MIMO and so on. SISO stands for single input, single output link. You have one transmitter, one receiver. And multi-input, single output, multiple transmitters, one receiver. And we have the beamforming, what we call as, you have a single user, you have multiple antenna. What you do, you just align the phase of the signal transmitted by the antenna such a way that the signal is constructively adding in a particular direction. That is called a virtual beam. All of them are transmitting, they add each other in the air, but you align the complex values of the x1, x2, x3, x4 in such a way that they align in such a way that they constructively add towards a particular user. So that is virtually like a beam of light towards a user. And of course, if you are good at signal processing, you can make multi-user MIMO, where you can have multiple beams towards multiple users. Okay, now we have come with the massive MIMO, just a quick summary of that. And I think I have discussed all these points. And some of the disadvantages are like high power consumption, hardware cost. Deploying so many antennas in that is a bit challenging. Anyway, there are ways to come out of it. And the other points I have already discussed, which are summarized in the slides. And one of the main aspects of massive MIMO is that sparsity of the channel. Okay, let me come back to the notion of sparsity. The term sparse tells you that, for example, if you think of a vector is said to be sparse if the number of non-zero entries in the vector is far less than the dimension of the vector. That is what called sparse vector. I have a lot of interesting stuff on this subject in the tomorrow's lecture, where we are going to learn about broadband spectrum sensing and spectrum sensing for fading channels, eigenspectrum sensing, and then so on. We have some interesting stuff in tomorrow's lecture on the sensing part. The spectrum sensing, we have the wide employment of the framework which is referred to as compressive sensing. So yeah, in the compressive sensing part, we will deal with the sparsity in detail. But just I have wanted to introduce the term, but the very details about the sparsity, compressive sensing and the recovery, all those things will come in the tomorrow's lecture. Okay, and it's a very interesting sub-Nyquist sampling technique. We will come to that. Essentially, like what happens, the millimeter wave operation with the massive MIMO that leads to the something known as sparse nature in the channels, either in the time or frequency. That is because of the attenuation and scattering nature of the millimeter wave signals. So what is advantage? Once you have a sparse vector in your problem, what happens, like you have some room to employ compressive sensing framework. So that is how again, one of the other handy support comes from the engineering and mathematics side is that CS framework. Originally, the compressive sensing was developed for image processing. We will see that in the tomorrow in detail. But this millimeter wave massive MIMO automatically paves the way for you to employ those things, those techniques in your communication path. I have some chat. Let me check if it is that something about the questions. Yeah, actually there is one thing, microwave length is not a centimeters, slightly. That can go up to meters depending on the band you are operating. Yeah. Voice is not clear, yes. Sometimes I hope it is fine now. I see some fluctuation in my internet. And so far my audio is clear.
Yes, sir.
Yeah, okay. If there is a very abrupt transition, just give me a call or text me here. Yeah.
Okay, sir.
Okay, spatial modulation. Probably in this lecture, I have few slides about that. Yeah. Okay, so let me continue then. What are the cellular communication aspect in the millimeter wave band? One is like we can go up to gigabits per rate and smaller wavelength and beamforming. I think I have summarized all these points to you. And let me go to the part slightly some mathematical details. I hope some of the equations subsequently many of you may not be clear, but I wanted to address those who are pursuing research as well in this area. So let me try to put it as layman terms, but that we have the receiver, okay, and I have say NT transmit antennas and NR receive antennas. Now the channel between them is represented by a matrix with a matrix H. H is like a NR cross NT matrix, meaning that NR cross NT matrix, that is taking NT size input from the transmitter, that is providing NR size output. So that is the dimension matching for that. So any channel entries, every entry of H is R comma T, meaning that if you have H3 comma 2, that tells you that the coefficient between the 3 comma 2 tells you that second antenna to third transmitter. So that is how the entries are filled up. Now what will happen if you think of a precoder, like before you transmit the signal, if you do some kind of precoding and with a matrix F and do another precoding with the matrix W in the receiver, is there any benefit of doing that? That is what the transmit and receive combining. And sometimes this is known as precoder. Now in the 5G technology and the other terminology, that is referred to as the beamforming, transmit beamforming and receive beamform. And okay, how to design or decide on the F and W? What is the best way? For example, instead of transmitting the signal X directly, you multiply with the matrix F and then transmit. Instead of operating directly on Y, you multiply by matrix W and work on it. Now the question is, what is the best combination or best pair, F comma W? The answer is lying in the part of which is known as singular value decomposition. Hope you might have come across SVD. So SVD has a lot of applications. Essentially, SVD is nothing but decomposing the matrix into product of three matrices, U, delta, lambda or V, and V Hermitian, and U and V are orthonormal matrices. If you have something about linear algebra background, let me not go into that. Essentially, that tells you that epsilon is a diagonal matrix. Diagonal in the sense that it has only all the diagonal entries, all entries are 0. So if you make the transmit precoder as V and receive precoder as W, then finally received vector will be epsilon times S plus N. What will happen? The effect, let me just show the effect of this. This is indirectly that first antenna to first antenna, second antenna to second antenna, and so on. So all your data is split and nicely going and sitting in the receiver. That is what the effective processing is the one. Play with some values and see how that can help me in effective reception of the signal. Starting from this SVD application, we have a lot of things to do with the multiple transmit and multiple receive antennas. One such thing is now we refer that to as beamforming. Essentially, beamforming refers to that. What is N? This is N stands for the noise, Gaussian noise. Yeah. So in the analog beamforming, so what we call that as analog beamforming is that you don't have a, I think I have to tell you some more thing about the baseband, DAC, RF chain, and so on. Let me come back to that. If you see a phase shifter like that, means that simply you can change the phase of the signal. For example, if you have a sine wave incoming, you put the phase shifter to 30 degree means that it will slightly delay the signal 1/6 of the wave whole part and then transmit with the antenna. Now, one RF chain, one DAC, one baseband processing. Actually, this chain is more costly compared to this phase shifter. Phase shifter can be implemented easily, but again, that depends on which bandwidth you are employing the phase shifter. If you are having a very high frequency and employ a phase shifter, it's slightly difficult. But nonetheless, compared to the RF chain and digital to analog converter and baseband processing, the analog phase shifters are less costly. But I cannot go into the details of that, but I can simply tell you with an example. Suppose that if you have an array of antennas, okay, if you make these phase shifter values to a particular, say theta is equal to 30 degree, without going to the mathematical details, I just tell you that if you simply turn the probe to 30 degree, then automatically all the antennas will be virtually looking towards a direction 30 degree from the vertical line. So that is equivalent to you are looking, for example, if someone is speaking from your left side or right side, you will turn your ear or head slightly towards them, right? This is something similar to that. Your antennas are listening virtually listening to a particular direction. That is what the role of this phase shift is. Meaning that if you have this kind of structure and if you align them in a correct way, the signal's gain will be very high in that particular direction for which you are looking for. And the other side that will ignore. Ignore means as much as possible. So that is what we call it as beamforming. So we have both transmitter beamforming and receiver beamforming. Meaning that either we can make all the antenna to transmit their energy in a particular direction, or we can make this antenna to receive the signal from the particular direction. So what should happen? The transmitter and the receiver has to align the direction of transmission and reception to have maximum bandwidth. That is what we call as transmitter and receive beamforming. Now, this is the technique. Like every antenna is looking forward, creating a beam towards a direction. Receiver also aligning its beam to receive the signal, transmitter and the beam, right? The analog beamforming refers to that, all these implemented with the phase shifters, right? Now what is digital beamforming? For every antenna, you have one dedicated RF chain. Direction of arrival, direction of departure, how we apply. Okay, a slightly technical question. Let me address this at last. Yeah. Okay, so to give you the notion of it, if you align, okay, to who are already familiar with this, if you make 1 e power j 2 pi by lambda pi by 6, e power j 2 pi by lambda 2 times pi by 6 and so on. If you align all the values like that, this will pick up the signal from 30 degree. Essentially, that is like 1 and slightly 30 degree shifted, 2 into 30 degree and so on. If you make all the complex values with multiples of j 2 pi by lambda times d sine theta, that will pick up the signal in the direction. Since I am addressing a wide range of audience, I skipped all the mathematical details. If you are interested, feel free to contact me later. And what is digital beamforming is, for every antenna you are having a dedicated RF chain. Meaning that you have a DAC, you have RF chain for every one antenna. So what is advantage of that? Like if you operate like that, you have more control over the beam rather than the analog beamforming. Compared to the analog beamforming with the analog phase shifters, you are having a much control over the beam when you operate with the digital beamformer. Digital beamformer is nothing but not only phase shift, it has a m e power j5, meaning that you can control over both the magnitude and phase of the signal. That is for the digital beamformer. So you have much control over the beam and make it effectively. But the problem is every antenna requires every RF chain. Okay, so what? The most power hungry device in your mobile phone is the RF chain. Okay, if you simply put your mobile phone in the flight mode, that can last at least more than 1 day, full complete day, or at least 4 times than your typical usage. Because the RF chains are the most power hungry devices in the mobile. Now, how many RF chains you need in your mobile phone? You have 2 antennas, so you need 2 RF chains. But if you go for millimeter wave, you have 1000 antenna. Can you employ 1000 RF chains in a single board? Point number 1, that is very much challenging. Second point, it is very costly in terms of hardware. And also that having so many power amplifier, low noise amplifier successively with 1000 antennas, that will create a lot of EMI, EMC problem, meaning that electromagnetic interference and compatibility issues. So designing the chip, that is something about the antenna design part, but still I want to tell you that it is not that much straightforward to place 100 RF chains within a smaller region, that too in a very high frequency. That's a quite challenging task. So what? Then go for hybrid beamforming. So what we are having in the analog beamforming and digital beamforming is that analog is fully with the phase shifter part, digital is fully with every antenna has one RF chain, right? But the analog beamforming, you have only one RF chain, multiple antennas. Okay. Now why don't we combine these two, analog and digital beamforming? That is what the hybrid beamforming technique we will going to see about that. Okay. I think this, let me go quickly faster. I have to tell you a few more things. Now we are going for the hybrid arrays, where we have the combination of both analog and digital part. That is what this. Instead of having only one single RF chain, what you are having multiple RF chain, but not equal to number of transmit antennas. See, for example, you have 1000 antennas, you have only say 10 or 20 RF chains. So every antenna will be connected to 100 antennas. Every RF chain will be connected to 100 antennas. So you are making a hybrid of fully analog beamforming versus fully digital beamforming. You just combine these two. Then what will happen? You are coming the notion of the hybrid beamforming structure. So that has a lot of advantages and give you the trade-off between the complexity, power efficiency, and the resolution of the beam. Okay, so how you can arrange your antenna? I think this is very interesting direction if you are working in this kind of antenna pattern design and gain and how to control the beamforming direction of and so on. For example, if you have interleaved array, you might be having different antenna arrays, every color operating at a different frequency band. So depending on how do you arrange it, the antenna beam pattern, if you plot in the chart, that will be completely different. How do you arrange these antenna arrays? So giving a complete research on how to arrange this antenna pattern, the smart antenna technique is one interesting line of research. And of course, I would recommend those who are working in that area, if you check in the Samir website, they have a lot of project how to design the smart antennas for the 5G. And recently, Bharat Electronics Limited also released one set of proposals in this antenna technique side. So if many doctorates will be here, I guess, I think you can look at the website for more details on the project call for along these lines. And it's still, they are open, I think. Yeah, this is what I'm trying to convey with the picture. So this is the beam pattern. After you plot with the processing and so on with the chart, the so-called normalized array factor. Like, so if you have to minimize the side lobes, you have to arrange these antenna arrays in a particular way. So how to arrange it, all these things play a role. Compared to red color, you can have a hybrid array and sub array and so on. Anyway, I just leave the reference to you. If you are working in the side, please do refer the literature and so on. And as I already said, the most difficult part is the hardware architecture. You have an attenuator, you have a low noise amplifier, you have a band pass filter, conversion to IF section, from RF section to the low noise. So this is the input antenna. You have to look from the right to left. This is the direction the signal flows in. So this one complete line is called one RF chain. So if you are doing for a digital beamformer, you need every antenna, you need complete one chain. If you are having a hybrid structure, for multiple antennas, you have one single chain. So that is how the analog and digital beamformer and hybrid architectures work. Right. And yeah, I think as I already said, some of the smart antenna techniques, please have a look at the hybrid structures, how to improve the spatial discrimination, meaning that how you have to be very focused on a particular direction. And yeah, how to estimate angle of, I think one of the participants asked about an angle of arrival estimation, angle of departure estimate. So with the hybrid number of antennas, how to create the beam, how to suppress the side lobes. The side lobes only tells you how much accuracy you are towards a particular direction. And of course, if you work nicely with the signal processing, not only a single beam, with many antenna, you can create multiple beams. That is what referred to as multiple beam processing. And of course, you can achieve spatial diversity, and you can estimate the angle of arrival, meaning that if you have to predict a signal from which direction that is coming from in terms of radar applications and so on. So the AOE estimate comes into the picture. And please do refer the sources I have given. You can get a lot of other information if you are working in that area. Like, there are several techniques for the AOE estimation, like beam scanning technique and the spectrum analysis technique and ML detector and so on. So all of these techniques give you one different direction to check it out. I think I have some more details about the received signal model. I think I have 10 more minutes left. And okay, I leave the rest of the slides, around 10 slides I have from now on. I leave it to the audience. Please have a look at it and feel free to drop me an email if you have any questions from that. Yeah, let me open to questions now for 10 more minutes, and let me have a break and we will meet again in the next session. Yeah, I open the questions to you.
Yes, sir. Thank you.
Participants?
అంత పెద్ద ఫార్మాట్ ఉంది కదా.
Sir, your audio is not clear.
Mine or?
No, sir.
Okay.
Some participant is asking some questions.
They can type the question if they want, and yeah, sure.
Participants, type your question in the chat box, please.
Yeah, so I read two questions for the suggest some resource for learning about massive MIMO and millimeter wave. Yes, and along with the slide, I will put one slide with all the references, some good reference for the starting point. Advanced pre-coding techniques, yeah, I will do the same for the two topics and put in the slides some references at last before I forwarding that to you. And more interestingly, if you have MathWorks, just you go for MathWorks website. Let me type here, mathworks.in. If you go there, check for 5G toolbox, the documentation. You will get a lot of information to that. I think
ఇందులో రివర్ట్ చేస్తాను అంటున్నా.
I'm not understanding the question clearly. Why are researchers not accepting the
Any
reproducibility?
more questions from the audience? Okay, sir.
Yeah. Okay then. So then let us meet at 11:30. Professor Kiran.
Sir, excuse me, sir.
Yeah. Shall we meet again at 11:30 for the next session?
11:30, sir. Okay, sir. Thank you for your informative session, sir. We will meet at 11:30.
Yeah, sure.
Thank you so much, sir.
Thank you very much. My pleasure.